So we've been talking lately about the idea of solutions, aqueous solutions in particular, things dissolved in water. And one of the topics that we have discussed is how we can quantitate the amount of a solute that's dissolved in our solvent, our water. And in particular, we've talked a lot about ions, ionic compounds. We're going to talk today about, or in this problem, about how to quantitate the amount of a compound. And I said before about the idea that we've been sort of been approaching this, looking a lot at ions, and it doesn't have to be ions. The solute doesn't have to be an ion, doesn't have to be an ionic compound. Covalent compounds will dissolve just as well. It's just that we are going to hit on a lot of topics that are relevant to ionic compounds in this chapter. And so when we're talking about molarity, we are going to be looking at not only ionic compounds but covalent compounds. Anything that will dissolve in a solvent, we can calculate a molarity for. And a molarity just tells us how many moles are in a liter of that solution. So it gives us an idea of how much has been dissolved. So what we're going to look at is our capital M molarity, which is moles of solute over liters of solvent. And so in this problem, we're looking at potassium chromate, and we want to determine what the molarity of this solution of potassium chromate would be. And so because we're given how many grams are dissolved in a certain number of milliliters, we're going to have to calculate how many moles of potassium chromate we would have and how many liters of solution that we're going to end up with. So there are going to be two small conversion problems that are going to go into this molarity equation, and you'll see we'll end up with the molarity when we're done with that. So the first one is we need to know what the moles of solute are. And we're starting with 0.275 grams potassium chromate. And what we want to do is we want to convert those grams to moles. So we want to calculate how many moles of potassium chromate we are dissolving in this solution to make the 500 milliliters of it. So what we need is we need to know how many grams of potassium chromate are in 1 mole. And we know already how to calculate molar masses. We're given the formula in the problem, so you can calculate exactly to high confidence what the molar mass would be. And for potassium chromate, it's 194.20 grams. Grams cross out, we're left with moles of potassium chromate, and we end up with 1.4161 times 10 to the minus third moles of K2CrO4. So we've calculated the top portion of this equation, the moles. Now we need to calculate the liters. This one should be a little bit more straightforward. I guess a little bit more comfortable for you because you've seen it a few more times this semester than you've seen the mole conversion, although hopefully by now the mole conversion is pretty comfortable to you as well. And we want to make 500.0 milliliters of this solution. Well, we need to know how many liters of that solution we will have. And so 1,000 milliliters in 1 liter. So the milliliters cross out, and you end up with 0.5 liters of solution. Oh, there is one thing that you have to be a little careful of, and I've actually fallen into the trap of it already in this problem, is this liters of solvent should really be liters of solution. So if you think about this and how this particular compound is made, that terminology actually does matter. And you wouldn't necessarily think it would, but I want to take a second to describe, because I made this error, I want to take a second to describe why it actually matters. So imagine that we're making this solution, and generally we make solutions in volumetric flasks. We talk about the idea of a volumetric flask in class. You'll use them in lab quite a few times. They're containers that will contain a specific solution. So in this case, if we're making 500 milliliters, we would take a 500 milliliter volumetric flask. Next thing we would do is we would take our 0.275 grams and we would transfer it into this particular container. So ideally what we would do is in a beaker we would place the 0.275 grams of our K2CrO4 and then use a small amount of solvent to dissolve that. So we'd add a little bit of water. You might say, how much water would we add? Well, as long as it's less than 500 milliliters, significantly less than 500 milliliters, it doesn't really matter. Enough to dissolve it, because then when that's dissolved, we can transfer it into that volumetric flask. So now that solution is there in the bottom. And what you'll find is on the neck of a volumetric flask is a little calibration mark, a very faint line at the top, and whenever we have liquid in there, until the meniscus rests on the bottom of that line, then that container will hold 500 milliliters, very precisely, to a very high confidence. So we would just start adding water to this till the meniscus was resting right on that line, and we would have 500 milliliters of this solution of potassium chromate. Now, to get back to the solvent versus solution problem, what we're going to find is that we actually would have added a little bit less than 500 milliliters to this volumetric flask. And the reason for that is that the volume of that solid that we're dissolving isn't zero. It has some volume to it. So we're actually going to be adding liquid until the solution is 500 milliliters, but we're going to be adding a little bit less than 500 milliliters of solvent. So in some ways, you get kind of embarrassed about making the mistake, but in other ways, it helps me to define the difference between those two terms. And it's very important that we distinguish between the two, because we want to end up with 500 milliliters of solution, not having added 500 milliliters of solvent. Okay? So now we have our two terms. We can get back to the problem that we were dealing with, and I'm going to move it over here a little bit. Got moles of solute, 1.4161 times 10 to the minus 3 moles. And we've got the 0.5000 liters. Think about significant figures. 0.275 grams has 3 significant figures. This has 5. As we take it from the periodic table, remember 2 decimal places. So we end up with a number that should have 3 significant figures. And then we've got our 500 milliliters. That's 4 significant figures. This is exact, so our volume total ends up being 4 significant figures. So 3 and 4. And when you calculate that molarity, you should end up with 2.83 times 10 to the minus 3rd molar, 3 significant figures from the 3, and that's our answer. Now, this is a straightforward way to express or use molarity or calculate molarity. We're going to find that dilution is going to be a little more complex than that.